Right. Brian, thank you for the introduction, the kind words. Um, so I'll be presenting the work we did for the Kaggle challenge, the passenger training challenge. I entered that competition with a teammate, Thomas Anthony. We're co-partners in our lab at the university. And the outline for the presentation is basically I'll provide a brief summary of the challenge, the problem, the data, and then I'll go into a background, a very high-level overview of machine learning and convolutional neural networks and recurrent neural networks. Those were the two architectures we used for our competition. And I'll go over the approach and our results. So the Kaggle challenge was a very interesting challenge. It's one of the was one of the largest competitions on Kaggle in terms of the the prize pool, and it also had a lot of controversy, but it was a very interesting problem. Um, the data set we were provided was from what they call the millimeter wave scanners that they have installed at the airport. And what these scanners do is that they send a low dose radiation that is enough to penetrate clothing, but not enough to penetrate the skin and human tissue. So they're able to see what is underneath your clothing, basically. So they're able to create a three-dimensional view of the surface. If you have things like pockets or weapons or guns, um, they're able to create three-dimensional images that can see threats on their clothing. So that was the data set, and they provided us various modalities of the data. Um, uh, the APS modality was 16 two-dimensional images. You can think of them as just images of the subject being scanned. So you see, yeah, the sequence of images kind of looks like a camera took a picture from 90 2.3 93 points of view of the person. So you have 16 images kind of looking around the subject. The second that they gave us was a 64 projection data set of the A3D APS, which provided 64 projections. And um, the third modality of data they gave us was the actual three-dimensional volume of the scan. And they also provided the raw sensor data, which is basically the raw signal captured from the machine. In order to use the raw signal, a team would have had to reconstruct the actual viewable image data from the raw image. So many teams in that challenge did not have the knowledge or the experience to actually use that raw sensor data. And as a matter of fact, most of the top teams use the 16 projection image. So one of the motivations for me entering this competition was that in my work in my PhD program, I was working with three-dimensional CT data and MRI data, and this presented a great opportunity to come and to evaluate some of the ideas we had been thinking about on those medical problems. So for a high-level overview of our approach, we utilize convolutional and recurrent neural networks, and our best model was sufficient to place us in third place. So this slide shows a high-level idea or a high-level framework of machine learning. So in machine learning, many supervised learning problems boil down to maximum likelihood estimation, where are given a a training set, you're trying to estimate the parameters of a model that correctly assigns the correct class label to every training sample in your data set. And this general framework can be applied to all kinds of machine learning problems. In deep learning, the theta in this log likelihood equation are the parameters of your network. In deep learning, those parameters are captured or represented in neural networks, right? So we try to find the parameters of a neural network that fits our data set. And we do this with stochastic gradient descent. So that is just the general framework for machine learning. And deep learning is just a subset where the parameters we're trying to find are captured in neural networks. So convolutional neural networks was one of the architectures we utilized in the challenge. And convolutional neural networks are made up of convolutional layers, pooling layers, normalization layers, and activation functions. And like I said in the previous slide, convolutional neural networks are just the realization of that theta parameter that captures that captures the parameters of our model. And the pioneering work on these convolutional neural networks was done in the 90s, in the 1990s, a long time ago. And Jan LeCun was the one that did the pioneering work, and he created a small network that was used to identify digits in the post office, and it worked relatively well. But convolutional neural networks didn't get a lot of attention from the computer vision community until 2012, when AlexNet won the first ImageNet competition. And you might ask yourself, why was there such a big gap between when people actually knew about convolutional neural networks and why is there a lot of buzz about it today? And the reason is they were very difficult to train from, say, mid-90s to early 2012, 2011, 2012. And the reason is that nobody really fully understood why they were difficult to train. Even Jeff Hinton, a lot of you might know Jeff Hinton, he came up with a scheme where you try to train neural networks one layer at a time, and you stack them. You train one layer, you freeze the weights, you train another layer. And he was doing this training procedures to alleviate some of the difficulties people had training deep neural networks. And insights into the problem came about when there was a paper by Yoshio Bengio titled "The Difficulties of Training Neural Networks." And in that paper, he revealed that a dominant activation function that they used in neural network during this period was called this Boydell activation function. And it suffered from this problem of saturation, where the activation, when you start optimizing the network, your activation values fall in a region where the gradients that are computed during gradient descent are zero. So what that led to is that the network oscillates. It doesn't learn a useful error signal. And he came up with a scheme to initialize the weights that of your network that prevented this saturation phenomenon. And this is my opinion. Okay, so and that gave insight into activation functions as a important part of training neural networks. And at about between 2010 and 2012, Jeff Hinton and his students came up with this ReLU activation function that does not saturate. And in my opinion, the main contribution But the main reason why deep learning and AI is taken up today is because of the introduction of the ReLU and the use of GPUs to compute, to learn, or to train networks. So there are a lot of papers between then and now talking about different things going on and this and that. The main contributions, in my opinion, are the ReLU activation function and the use of GPUs. So over the years, from 2012 to now, there has been continuous improvement in convolutional neural networks for computer vision. From AlexNet won the competition in 2012, and that steered the whole computer vision community towards using convolutional neural networks. The AlexNet breakthrough it used was the ReLU activation functions. It was a very tiny 5 or 8 layer network. It used the ReLU and dropout, and that was about it. And it beat next performing network or approach by such a wide margin that the whole computer vision community started looking into convolutional neural networks. And the next improvement in performance on the ImageNet competition was something called ZFNet. And the ZFNet won the ImageNet competition in 2013. And the improvement that ZFNet made over AlexNet was that the creator of ZFNet observed that if you reduce the filter kernel size, the filter kernels are what learns the features in your images. So if you use large feature kernels, you learn coarse features. If you use smaller feature kernels, you learn fine features. So you found that those large feature kernels that were used in AlexNet were causing the network to miss useful information. So he reduced the kernel size and he made the network a little bit deeper, and that improved the performance. And the next big improvement was the Google network, right? By Google, they came up with an architecture that there's a lot of, it's called the inception module. And if you look at the inception module closely, you'll realize that they are also playing a trick on the kernel size. So they combined multiple kernel sizes like 3x3, 5x5, 7x7 filter kernels in a single layer to learn features at various scales. So in all the advances of convolutional neural network, you realize that the improvements have been based by very simple and subtle observations from the prior work of others, and drowned in all the noise on deep learning and the papers. The main contributions have been the non-saturating linear activation functions, the filter kernel size used in the architecture, and the depths of the network. And I think right now in computer vision, we've reached a point of diminishing returns where the only way to do better than a ResNet is to ensemble your model. So that is the background on convolutional neural networks. And the architecture we used in the Kaggle challenge was the ResNet. So let me move on to the next slide. So the other architecture we used for challenge was a recurrent neural network. And at a high level, recurrent neural networks have a notion of memory, meaning they, unlike convolutional neural networks where you feed in an image or you feed in the input and you get the response, recurrent neural network have the notion of memory. So they're good at modeling things like language, text, sequences, and speech, things where you can make a decision about what to classify something as without considering what came before. So like sentences, for example, a single word could change the meaning of a sentence. So you have to factor in the words that came before. So they have this notion of memory. You feed in feed it a sequence, and it captures uses the human layer to capture history or state in a way. And this is the diagram here shows a simple illustration of a residual of a recurrent neural network. In practice, the architecture is a little more complicated. The long short-term memory LSTMs are often what is used in practice, and they're a little more complicated than the simple recurrent neural network shown here, but they have the ability to remember long sequences. So we use these two architectures in our Kaggle challenge, the convolutional and recurrent neural network. So this is a high-level description of our architecture. So like I said, we were provided 16 projections of an individual that was scanned, and that could be a threat. Say you had a threat on your back pocket. That threat might not be visible in all the projections. So in order to determine and use information across multiple projections, we used the CNN, the convolutional neural networks, as sort of feature extractors to learn, is there a threat in this frame of the data? We had 16 frames. You can think of it as 16 sentences. But instead of 16 sentences, we say, let's use a convolutional neural network to extract a feature vector from a given frame, and then use the recurrent neural network to correlate information from one frame to the next. Kind of how a human will look at something spinning and say, I see a thread on the left leg, and you correlate what you see from one frame to the other. The LSTM is able to learn the correlation from frame to frame. So this was an architecture we felt would work well for the challenge, given the way the data was structured and the modality of data we chose to use. In order to use that architecture I described in the previous slide, we needed to annotate the data in a more granular level. So this image kind of shows 16 frames. The label was given to us on a subject level. So what we had to do was we had to, in the training set, look at each of the frames and determine if a threat was visible, and then relabel the data. So this allowed us train a convolutional neural network to learn frame-based threats, and then a recurrent neural network to correlate the sequence of frames to aggregate sort of the results from the sequence of frames. So what you see here is sort of our two-phase training approach for the challenge. The first phase was where we trained a simple ResNet to act as a feature extractor on individual frames. And in the next phase, we train them jointly to learn the subject level threat. So one question one might have was that, why did you need the LSTM? Why couldn't you just aggregate predictions from, or aggregate predictions from individual frames into a single prediction? And the answer is we tried that, but the LSTM approach worked better. And we kind of think the LSTM internally learned some kind of temporal representation that gives it some sort of advantage in this kind of sequence modeling problem. So this slide shows our results in the challenge. We trained many models. We trained ResNet 50s, Inceptions, Google Nets, Exceptions, VGG19s. We trained a lot of models, but consistently the ResNet 50 model outperformed all the other models. And particularly one one very interesting observation was that the ResNet 50, based on our training procedures, a single model was, or an ensemble of all our models was only very slightly better than our single ResNet 50 model. And that was quite interesting, because that has huge significance for production deployments of neural networks. It reduces the amount of resources you might need to deploy a production model if you don't have to assemble too many models. So our architecture was based on, for training, was based on, we used 4 P100 GPUs, which is, because the data was fairly large, it was a lot of data. So we did multi-GPU training for the problem. And that kind of helped us out a little bit in terms of training time. So I'll conclude the presentation here and switch back to. So is Bio taking over, or are there any questions? Did you see my slides? Hello? Can you hear me?
Hello? Hello?
Yes.
Sorry, we couldn't see the slides.
You couldn't see the slides?
No, so it was not on projection. So we only saw just one page, page 1.
Okay, let me try to project this again.
That one is the library.
Okay. Can you see the slides now?
Yes, we can. Oh, it's off. Yes, we can.
Is it clear?
Yes, but you need to zoom. You need to move to full screen. Okay, so you can. Yes, it's now clear.
Okay, so you don't mind me running through it again?
Yes, we don't mind. We don't mind. It's a pleasure.
Okay. So sorry about that. I didn't know the slides were not visible. So I'll go over the presentation again. And so as I discussed earlier, now Kaggle provided us data sets for the challenge. The passenger screening challenge was the largest in terms of prize pool at $1.5 million. They provided us data in 4 different modalities: an APS data set where we had 16 projections of the image. A second data set was the 64 projection data set, and these are just simple images, 2D projections. A third was a 3D volume that was a volumetric data set, and the last was a raw scanner sensor data where you had to reconstruct the image with if you wanted to use that one. Many teams did not use the raw sensor data. They utilized, in fact, a lot of the top winning teams used the 16 projection, 2-dimensional projection image. So for the challenge, as I said earlier, we utilized convolutional and recurrent neural networks. And our best performing single model was sufficient to place us in 3rd place. So many supervised learning algorithms can be reduced to maximum likelihood estimation, where you try to estimate the parameters data of a model uh, um, that assigns some probability distribution to the data or to a target space. And the idea is to solve for the parameters of your model that fits your training set. And this general framework allows deep learning also fits into this general framework where your parameters data are captured in a deep neural network. So the way you find the parameters is through stochastic gradient descent. It's an iterative algorithm that tries to find the optimal parameters. Convolutional neural networks, as I discussed earlier, are composed of convolutional layers, max pooling layers, normalization layers, and ReLU activation. And the pioneering work on convolutional neural networks was done by Yann LeCun in the 90s. And between 90 and 2012, or the mid 90s, when he initially proposed convolutional neural networks, there was not a lot of activity, or it wasn't heavily adopted by the computer vision community. And part of it was because of difficulties training neural networks. And in the between like 2000 and 2010, a lot of researchers like Yoshua Bengio, Jeff Hinton, they tried various things to optimize neural networks, but ultimately the output of their effort was the introduction of the ReLU activation function that enabled training deep convolutional neural networks without layer-wise pre-training or things like that, and the advancement of GPU computing that enabled you to train larger networks. So 2012 was when the computer vision community adopted convolutional neural networks as the model for computer vision. And since then, the ImageNet competition has been a benchmark for the performance of various convolutional neural network architectures. And the improvement in the network architectures has been driven by depth, deeper, bigger networks, and by filter kernel size. And this is my opinion. It's not. This is what I think when I look at the architectures. This is what I think has fundamentally made one architecture better than another. The other architecture we use are the recurrent neural networks. Recurrent neural networks have the notion of memory. They enable you to learn sequences. They're good for things like speech modeling, language modeling, and unlike convolutional neural networks, the output is dependent not only on the current input but on previous inputs. So the architecture we utilized for the challenge was one that combined convolutional and recurrent neural networks. We used the convolutional neural networks as feature extractors. So the convolutional layers are able to extract features from the projections were provided in the Kaggle challenge, and the LSTM, or recurrent neural network, correlates features across frames. And the benefit of this architecture is that it enabled us work with the data in 2 dimensions. CNN architectures are robust. 2-dimensional neural networks are robust. They are well tested. They've been benchmarked. They're good. So whenever you can reduce your data to an image, it makes designing an architecture for classification easier. And that's, even though our data came in 3 dimensions, working with it in 2 dimensions enabled us work with it with the available computational resources. In order to train that architecture, we needed to create frame level annotations on these 16 projections. And what that enables us to do is that we can train threat detection on a frame level like any other image classification problem. And then we can then aggregate across frames with our LSTM. Without training on frame level features, we found that it was difficult to optimize this combined LSTM CNN architecture. The optimization was difficult, but when we did pre-training of the CNN on frame levels, the convergence of our full architecture occurred. It was easier to train. So this slide presents our results. We trained many models, ResNets, exceptions, inceptions, and various VGG19s, various architectures, but our best performing model was the ResNet 50, and the single model was only slightly worse than the ensemble of all the models we trained. And for the architecture, we used 4 P100 GPUs, and it was a very big data set, and using multi-GPU training helped us out a lot. So I will conclude here.
Okay, thank you very much, sir. We really appreciate it.
Sorry about the, I couldn't hear you, so you probably were telling me you can't see the slide, but I was looking at the slide. Sorry about that.
Thank you very much, sir.
No problem.
So we are collecting the questions and about to send some of the questions to you, so you can. Somebody's.
So do I respond to the questions in chat, or are they coming across on chat? Or
Yes, I'm going to read them out once I get all the questions. I'm going to read them out to you, so you'll be able to answer them accordingly. So, sir.
okay.
Can you briefly explain the RELU activation concept?
Okay, so so the ReLU activation concept, it's a function that it's like a linear function, right? It's a straight line. And at one part, if the leaky ReLU or the ReLU, it's a straight line. So there's no point along this function where you cannot compute a derivative that is not 0. And there's no point greater than 0 that you can compute an activation greater than 0. But if you look at the sigmoid activation function, it kind of looks like an S. And there are parts of the function that are flat, right? I wish I could draw it, but they're part of the activation function that are flat. So if your network is in the flat region, if when you've computed the linear function of the inputs and the weights and the bias, and your activation function falls in the flat part of the function, when you compute the gradient, it's going to be 0. And if all your neurons are at this flat part of the function, when you're doing back propagation and the gradients are being computed, they're all going to produce 0 gradients, and that doesn't give any useful information for the network in optimization. right? So the network doesn't know, how do I update the weights of the network to improve the classification? So that's the idea behind the ReLU. And so the ReLU is always, you always get a useful derivative on the ReLU function. So your network always, when you run back propagation, the network always has an idea of which direction to go to optimize the weights of the network. So that's the basic idea between the ReLU, and you can Google the ReLU function. I'm sorry I didn't put a picture of the ReLU activation function on the slide, but the idea is that the ReLU, you can always compute a gradient with the ReLU, while the sigmoid activation function, if you are in a flat part of the function, the gradient is going to be 0. So when you're running backprop, your gradient signals are not going to produce useful information for your network. So that was the idea, and that was what Yoshua Benju realized was going on that was causing it to be difficult to optimize networks.
Okay, thank you very much for that, sir. There's another question in here that asks about how did you use the multi-GPU training? Because on Google Colab there's only a single GPU.
So we didn't train on Google Colab. My teammate is very good with high performance computing, so he built a machine with multi GPU. We did not use Google.
Okay, thank you very much, sir. Another question is, did you use probability or statistics approach in any way at all? If yes, how did you implement it?
Well, a neural network is a statistical approach. Maybe the statistics we used was in estimating the parameters for an ensemble. So that might have been where we used statistics, but mostly our approach was solely based on deep learning and optimization. So there was no classic machine learning in that sense, so we used an end-to-end deep learning based solution. Maybe the opportunity to introduce some probability or statistics was in determining the parameters for ensembling our models together, which was done with basic cross-validation.
Okay. Now another question for you is, he said pertaining to the CNN plus LSTM, very interesting. Can you do this for segmentation? Can LSTM process a sequence of segment marks?
LSTM for segmentation? I don't know. I don't know, but the general approach to segmentation is usually a CNN-based approaches, like the mask RCNN. The max RCNN, I don't know if there's, yeah, you might find a way to use an LSTM for segmentation, but I just can't think of one directly off my head right now.
Okay, someone is also asking that would they also be able to get the slides after the
presentation? Yeah, I'll think about that.
Okay, thank you very much.
Okay, that has been awesome session. I'm sure that the session has provided a lot of inspiration, a lot of people. I'm so sure that somebody is going to get out of this session to start something. David, before you leave, I think you just need to get some word from you. Someone who wants to get deep into image classification. What are the key starting points? What are the things you recommend as must have for a starter, especially in a part of the world where certain things are not available? Hi, David.
Hi, Baya. Sorry, I couldn't hear you clearly.
Okay, so I'm asking that, okay, good. Brilliant session, very inspirational, which is the objective of the session. So
Thank
if I want to, a student who wants to go into a classification of this level, what are the key starting points? For example, you spoke about your friend who had to do and how to performing computer. That is avant-garde. For somebody from our part of the world, emerging market and all that. What are the things to consider? What are the starting points? To be able to do things of this class. Because it's a mega project. Looking at the volume of the data. So what are the alternatives that are available? If I'm not able to have access or build high-performing computer, what are the starting points for me?
I agree. That is a major barrier. Is the discrepancy in access to sort of the resources. Like, yeah, I don't know how to answer that question. Um,
Okay.
but this competition by itself required a lot of resources. But there are many challenges that do not. Like a lot of the Kaggle challenges do not require. All you need is a laptop. You don't need a GPU. You don't need. There are many challenges where you can learn tremendous amount of information without requiring, the kind of computational resources that were used in this challenge.
You're very right. I think that's very right. So just that I'm so keen because quite a lot of work in our part of the world also requires images. We have students working, for
Yes.
example, on malaria detection. Quite a lot of work being done, street mapping, socioeconomic
And
balance.
and another point is that the cost of the GPUs themselves are coming down. And
Yeah,
if you can build a machine with a GPU, you don't have to pay Amazon or Google, the subscription fees to get access to the computing resources. Um, um, so the idea will be to get to build hardware. You can buy the GPUs off market and build the machines yourself. Um, I think the cost of the GPUs on the second hand market is coming down, specifically with the collapse of Bitcoin and other. Yeah.
Okay, thank you very much, sir.
Yeah.
There's just the last question. I sent it to you via the chat, but it's talking about for precision. It meant that using the pre-training CNN ResNet as you did, but to output a max instead of labels and all them to the LSTM as you did. That's what it was.
Oh, okay. Oh, I see what you're saying. Is you use but the LSTMs, yeah, it might be an experiment to try. Yeah. Sounds like an interesting.
Okay. Thank you very, very, very much, sir.
Thank you.
okay. Thank you very much, David.
Yeah, Bayo,
This
thank you. And I really admire the work you're doing with Data Science Nigeria. I think it's phenomenal. It's
Thank you very much, David. This has been a great session. Thanks to everyone who has given us the Saturday evening to join David. We want to especially thank David. He's only known every morning, noon in the US, having some breakout time with family to them to spend this time with us. Thank you so much, and we look forward for further collaboration. And of course, the opportunity to introduce some of our students who want to this year, we want to make classification to you. So that you can remotely invite and support them and also continue to inspire them. So thank you very much. As I round up, I just make a statement the vision of this science Nigeria to build world-class AI knowledge research ecosystem. Um, and also to scale up the capacity while building world-class AI knowledge, research, innovation ecosystem that delivers high impact. And we hope that we can get more Nigerians interested in AI, such that in 10 years we can reach 1 million AI talent. We have 200 million of people. Very, very interesting. So guys, you're looking for opportunity for deep learning. Like I said, we now run three classes, all categories of learning. We call it AI every day at our new AI hub in Yaba. Monday is for Monday and Thursday is for pre-university intro Python and ML class. So the students that finish your SSC, you are waiting for university admission, don't stay at home, don't waste your time at home. I spend 10 weeks on Monday and Thursday to learn. Tuesdays for deep learning class year masterclass. Wednesday Python with beginners class in machine learning. Friday is AI for good, where we look at use cases on AI for good. And Saturdays are business analysis for professionals, which run for 5 weeks and 9 inches. And this is paid for the Saturday one because it's more ranging professionals and experts in industry. All classes are on Monday to Friday are all free. And just get onto our website, follow us on Twitter or any of our social media links to be able to get more information about what we're doing. And of course, check us out on YouTube to see a lot of our videos, a lot of past classes, particularly the 100 days of machine learning. They're all available. And of course, as you get to the hub, we just have a library of books that can be used to do capacity. Like I said, I provided updates on the calendar, so I'm sure everybody will do everything they're going to take to make it there become 19th November to 23rd November. It's a place to be. But even if you're unable to make it, make sure you go to the 100 days of learning, participate in the Kaggle competition, and keep building yourself. We've had the story of David, it's a great story of inspiration. Guys, the future awaits us, and we can leverage AI to change the narrative of our country. We can be talents that can dominate in different fields, and we can make this country great again. So guys, thanks for joining us. You have a wonderful time, and let the learning continue. Have a wonderful weekend, and see you again when we come together for another AI Plus Masterclass with leading experts and David and everywhere in the world. Have a wonderful day. Bye.
All right. Again.
Bye. Thanks, David. Bye.